Chapter 5 Sources of Electricity. Every student knows the story of Benjamin Franklin and his kites. For centuries before Franklin, scientists and philosophers had observed lightning. It was thought the experimentation and research of Franklin that the relationship between lightning and static electricity was confirmed. What is electricity, and where does it come from? Years before the discovery of the electron theory by J.J. Thomson, it was suggested by Franklin that electricity consisted of many tiny particles, or electric charges. He further theorized that electrical charges were created by the distribution of electrical particles in nature. We have learned that a potential difference or electromotive force is created when the electrons are redistributed. A body might assume a charge. Its polarity is determined by the deficiency or excess of electrons. People have turned their scientific interests in research to the development of machines and processes that can cause an electrical imbalance and an electrical pressure. There are 6 basic sources of electricity or electromotive force. They are friction, chemical action, light, heat, pressure, and magnetism. In this chapter, we will discuss in detail producing electricity from chemical action or batteries. You will also learn how electricity is produced using light, solar batteries, pressure, and heat. 5.1 Chemical action. One of the most familiar sources of an electrical potential or voltage is the battery. In 1790, the Italian scientist Luigi Galvani observed a strange phenomenon during the dissection of a frog supported on copper wires. Each time he touched the frog with his steel scalpel, its leg would twitch. Galvani reasoned that the frog's legs contained electricity. Alessandro Volta, another Italian scientist, invented the electric cell, named in his honor, called the Voltaic Cell. The unit of electrical pressure, the volt, is also named in his honor. Volta discovered that when 2 dissimilar elements were placed in a chemical that acted upon them, an electrical potential was built up between them. Thus, electricity can be produced by chemical action. The student can construct several voltaic cells to demonstrate this action. Cut in a 1-inch square of blotting paper and soak it in a strong salt solution. Place the wet paper between the penny and the nickel as shown in figure 5-1. If a sensitive meter is connected to the coins, it will indicate that a small voltage is present. In figure 5-2, electricity is created using a grapefruit. Make small cuts in the skin of a grapefruit. In one cut, place a penny. In the other cut, place a nickel. Once again, a meter will indicate that a small voltage is present. A better cell can be made by placing a carbon rod. These may be removed from an old dry cell and a strip of zinc in a glass jar containing an acid and water solution. Figure 5-2 all safety precautions when performing experiments. In figure 5-1, a simple cell is produced using a nickel and a penny and a salt solution. In figure 5-2, a grapefruit can be used to produce enough electricity to operate a small radio. Lesson in safety. When mixing acid and water, always pour acid into the water. Never pour water into the acid. Acid will burn your hands and your clothing. Wash your hands at once and clean water if you spill acid on them. Acid may be neutralized with baking soda. See your instructor for first aid. Figure 5-3. This experimental cell made with zinc, carbon, and acid produces enough electricity to power the light. When the polarity of the carbon rod is tested, it will be positive. The zinc strip is negative. If a wire is connected between these 2 elements or electrodes, a current will flow. A voltaic cell can be described as a way of converting chemical energy into electrical energy. The zinc-carbon example of a Voltaic cell, the sulfuric acid H2SO4 and water H2O solution, is also known as an electrolyte. When the electrodes are placed in this acid electrolyte, a chemical action takes place. The sulfuric acid breaks down into the positive ions 2H plus and negative ions SO4, 2 to the negative. The negative ions move toward the zinc electrode and combine with it by making zinc sulfate, ZnSO4. The positive ions move toward the carbon electrode. This action creates a potential difference between the electrodes. The zinc will be negative, the carbon will be positive. This cell will develop at about 1.5 volts. If a load such as light is connected to the cell, a current flows and the light glows, as seen in figure 5-3. As the cell is used, the chemical action continues until the zinc electrode is consumed. The chemical equation for this action is the following: Zn plus H2SO4 plus H2O is transferred to ZnSO4 plus H2O plus H2, which increases. Zinc plus sulfuric acid plus water chemically reacts to form zinc sulfate and water and free hydrogen gas. This cell cannot be recharged because the zinc has been consumed. Primary cells. The zinc-carbon cell described in what is known as a primary cell. A primary cell is a cell in which the chemical action cannot be reversed. A primary cell cannot be recharged. Defects in the primary cell. One might think that the chemical action of the zinc-carbon primary cell would continue to produce voltage as long as the active ingredients of the cell are present. In studying the equation for the discharge of the cell, you will observe the formation of free hydrogen gas. Since the carbon electrode does not enter into chemical action, the hydrogen gas has bubbles. The hydrogen forms gas bubbles. These collect around the carbon electrode. As the cell continues to discharge, an insulated blanket of bubbles forms around the carbon. This reduces the output and terminal voltage of the cell. The cell is said to be polarized. The action is called polarization. To overcome this defect in the simple Voltaic cell, a depolarizing agent can be added. Compounds that are rich in oxygen, such as manganese dioxide, MnO2, are used for this purpose. The oxygen in the depolarizer combines with the hydrogen bubbles and forms water. This chemical action appears as 2MnO2 plus H2 transferred to Mn2O3 plus H2O. The free hydrogen has been removed, so the cell will continue to produce voltage. One might assume that when the current is not being used from the cell, the chemical action would also stop. However, this is not true. During the smelting of zinc ore, not all impurities are removed. Small particles of carbon, iron, and other elements remain. These impurities act as the positive electrode for many small cells within the one large cell. This chemical action adds nothing to the electrical energy produced at the cell terminals. This action is called local action. It can be reduced by using pure zinc for the negative electrode, or by a process called amalgamation. With amalgamation, a small quantity of mercury is added to the zinc during manufacturing. As mercury is a heavy liquid, any impurities in the zinc will float on the surface of the mercury, causing them to leave the zinc surface. This process increases the life of a primary cell. Types of primary cells. There are many different primary cells. What follows are details on some of the most common primary cells you might encounter. Zinc-carbon cell. Although the primary cell has been described as a liquid cell, a liquid is not common use. Rather, the primary cell is often a dry cell. In a dry cell, the electrolyte is in a paste form as opposed to a liquid form. A dry cell averts the danger of spilling liquid acids. Flashlight battery cells are examples of dry cells. The dry cell consists of a zinc container that acts as the negative electrode. A carbon rod in the center is the positive electrode. Surrounding the rod is a paste made of ground carbon, manganese dioxide, and salt ammonium chloride, mixed with water. The depolarizer is the MnO2. The ground carbon increases the effectiveness of the cell by reducing its internal resistance. During discharge of the cell, water is formed. You may recall having difficulty removing dead cells from a flashlight. This is because the water produced caused the cells to expand. Although this problem has been resolved by improved manufacturing techniques, it is still not advisable to leave cells in your flashlight for long periods of time. You should keep fresh cells in your flashlight so it will be ready for emergency use. Lesson in safety: improper battery use can cause leakage and explosion. Therefore, obey the following precautions. Install the batteries with the positive and negative polarities in proper direction. Do not use new and old batteries together. Never attempt to short circuit, disassemble, or heat batteries. Do not throw batteries into a fire. Batteries can contain or do contain dangerous materials that should be recycled or disposed of properly. Contact your local recycling facility or fire department for more information. Alkaline cell. The alkaline batteries use manganese dioxide for the positive activating substance. Zinc powder is used as the negative activating substance. A caustic alkali is used for the electrolyte. Recent progress in electronic product design has demanded more compact supply sources. The number of products needing a large current and a long battery life have increased. This required the development of more advanced batteries. Cylindrical alkaline batteries are now widely used to supply power for electronic products. They can be used with common manganese dioxide batteries. See figures 5-4 and 5-5. Mercury Cell. A relatively new type of dry cell is shown in figure 5-6. It is called the Mercury Cell. It creates a voltage of 1.34 volts from the chemical action between the zinc negative and the mercuric oxide positive. It is costly to make. However, the Mercury Cell is better in that it creates about 5 times more current than the conventional dry cell. It also maintains its voltage under load for longer periods of operation. The Mercury Cell has found a wide use powering field instruments and portable communication systems. See figure 5-4, the AA alkaline cell, and figure 5-5, a cutaway of the AA battery size alkaline cell. The lithium cell. Lithium has the highest negative potential of all metals. It is therefore the best substance for an anode. Many battery makeups are possible by mixing lithium with various cathode substances. Energy densities of these batteries can be computed by respective reaction equations. Figure 5-7 shows the energy densities of lithium batteries compared to those with conventional batteries. Lithium is the most suitable anode for production of high voltage and lightweight batteries, referred to figure 5-8. In figure 5-6 we see a mercury cell. It creates a voltage by chemical action between the zinc and the mercuric oxide. Features of lithium batteries such as voltage and charge and discharge capacity are determined by the type of cathode substance used. Fluorocarbon is a intercalation inserted between or among existing elements compound. It is produced through reaction of carbon powder and fluorine gas, and it is expressed in CFN. The silver oxide cell. Silver oxide cells have several advantages over other types of cells. These advantages include very stable discharge voltage, excellent high discharge characteristics, high energy density per unit volume, wide range of operating temperatures, compact thin size. The compact silver oxide batteries have the highest electrical volume and leakage resistance of any battery of that size. They are commonly used in watches. Two types of silver oxide batteries are made for use in watches. One type uses caustic potash for electrolyte. The other uses caustic soda. The caustic potash battery has the symbol W on the bottom of the battery. It is for high drain use, where more power is needed. It is used with wristwatches with liquid crystal displays and multifunction analog watches. The caustic soda battery has the symbol SW on the bottom of the battery. It is for low drain use. It is used mostly in single function analog watches. Figure 5-9 shows a cutaway of a silver oxide cell. Nickel cadmium cell. The nickel cadmium cell is a rechargeable dry cell. Basically, these are nickel cadmium alkaline batteries with paste rather than liquid for the electrolyte. The ability to be recharged is just one of their advantages. Other advantages include long life, high efficiency, compactness, and lightweight. The nickel cadmium cells produces a high discharge current due to its low internal resistance. Other uses include the powering of small radios, burglar alarm systems, camera flashes, and aircraft instruments. See figure 5-12, the construction of a nickel cadmium cell. One type of nickel cadmium cell uses a positive and negative plates, a separator, alkaline electrolyte, and a metal case, and a sealing plate with self-releasing safety vent. It is shown in figure 5-12. The positive plate of this batteries is a porous powdered nickel base plate. It is filled with nickel hydroxide. The negative plate is a punched plate of thin steel coated with cadmium active material. The separator is made of polyamide fiber for high temperature uses. It is made of a non-woven polypropylene fiber. The positive plate separator and negative plate are pressed together, wound into a coil, and inserted in the metal case. The electrolyte is an alkaline aqueous solution. It is totally absorbed into the plate and the separator. The metal case is constructed of nickel plated steel. It is welded on the inside of the negative plate. It becomes a negative pole. The sealing plate uses a special liquid sealing agent to form a perfect seal. The positive plate is welded on the inside of the sealing plate. It becomes the positive pole. The self-resealing safety vent permits the discharge of the gas in the event of an abnormal increase of internal pressure. This prevents against rupture or other damages. The vent is made of a special alkaline and oxidation resistant rubber. This ensures that operating pressure and safety features will be retained over a long period of time. The electromechanical processes of a nickel cadmium alkaline cell are outlined below. See the formula at the bottom of page 89. In this process, charging and discharging are reversed in a very efficient manner. The electrical energy used during discharge is regained during the recharge. During the final charging stage, an oxygen gas is created with the reaction occurring at the positive. See the formula at the top of page 90. This oxygen passes through the separator to the negative. After this, an absorption reaction takes place at the negative and absorption occurs. See the formula again at the top of page 90. Nickel metal hydrate cell. Nickel metal hydrate, or NIM, is a rechargeable battery very similar to the NiCad or nickel cadmium battery. The NIM battery uses the nickel for the positive cathode and a hydrogen absorbing alloy for the negative anode rather than cadmium, which is found in the NiCad battery. The fact that NIM batteries do not use cadmium makes them environmentally friendly. Hydrogen absorbing alloys are made from combinations of nickel and iron, Fe, magnesium, Mg, and lithium, La. The alloys can absorb large volumes of hydrogen equal to approximately 1,000 times their weight without an increase in volume. This means the batteries can be sealed without the danger of explosion caused by expansion of materials. A NIM battery can have 2 to 3 times the storage capacity of a NiCad battery of equal size. This has made it an excellent battery for hybrid vehicles and portable computer applications. The discharge voltage level is 1.2 volts, which is the same as for NiCad batteries. The NIM batteries can be recharged over 500 times. The combined characteristics of the NIM battery makes it an ideal replacement for existing NiCad battery applications. NIM batteries should never be completely discharged. If they are, one or more of the cells can reverse polarity, which will result in permanent damage to the battery. Electronic devices that use NIM batteries typically have a special circuit designed to detect low voltage levels and then disconnect the battery circuit before damage can occur. Batteries in series and parallel. Often a single cell is called a battery. By strict definition, however, a battery consists of 2 or more cells connected together. These cells are enclosed in one case. Series connection. In the study of electricity, it is important to understand the purpose of and the result of connecting cells in groups. First, consider the series connection. In this method, the positive terminal of one cell is connected to the negative terminal of the second cell. In figure 5-13, 4 cells are connected in series. The output voltage will be equal. See the formula on the top of page 91. E out equals E one cell times the N, where N equals the number of cells. So, in the case of the battery shown, voltage out equals 1.5 volts times 4 equals 6 volts. Again, at the top of page 91. Notice that the voltage has increased 4 times. However, the capacity of the battery to supply a current is the same as one cell. Cells are connected in this manner to supply higher voltages for many uses. A flashlight may use 2 or more cells in series. Batteries for portable equipment have many cells in series to produce 6, 9 to 24 volts. The amperage does not increase by connecting cells in series. Parallel connection. In figure 5-14, the positive terminals have been connected together and the negative terminals have been connected together. These cells are connected in parallel. The voltage across the terminals of the battery is the same as only one cell. Although the voltage has not increased, the life of the battery has been increased because the current is drawn from all cells instead from just one. The amperage is added by connecting cells in parallel. See figure 5-13 now in top of page 91. A pictorial schematic diagram of 4 cells connected in series the voltages add when connected series. And 5.14 at the top of page 93. Schematic symbols, a pictorial and schematic diagram of 4 cells connected in parallel. This connection only provides 1.5 volts, but with 4 amps of current. And just quickly, as an interlude, experiment 5-1, page 90, bottom of page 90, voltage in series. In this experiment, you will demonstrate and observe how voltages add in series. The materials include 4 flashlight cells or D-types, 4 cell holders, and 1 multimeter. Step 1. Connect the 4 cells in series. See schematic in Exhibit 5-1A, bottom of page 90. Step 2. Set your multimeter to read voltages in the 0 volt to 10 volt range. Step 3. Measure and write down the voltage between the points A and B. Step 4. Measure and write down the voltages between points A and C. Step 5. Measure and write down the voltage between points A and D. Step 6. Measure and write down the voltage between points A and D and E. Do your results follow the formula for voltage sources in series? What conclusions can you draw from this experiment? Experiment 5-2, voltages in parallel, bottom of page 91. In this experiment, you will demonstrate and observe how voltages add in parallel. The materials include 4 flashlight cells, D-types, 4 cell holders, and 1 multimeter. Step 1. Connect the 4 cells in parallel. See the schematic in Exhibit 5-2A at the bottom of page 91. Step 2. Set your multimeter to read voltages between 0 volt and 10 volt range. Step 3. Measure and write down the voltage between points A and B. Step 4. Remove cell number 4. Measure and write down the voltage between points A and B. Step 5. Remove cell number 3. Do not replace cell number 4. Measure and write down the voltage between points A and B. Step 6. Remove cell number 2. Do not replace cells number 3 and number 4. Measure and write down the voltage between points A and B. Do your results follow the formula voltage sources in parallel? What conclusion can you draw from this experiment? Page 92, sound navigation ranging, or sonar. Sonar is an underwater detection system based on horizontally directed sound waves and their echo reception. Sonar operates on a principle similar to that of radar, but instead of electromagnetic waves, it uses sound waves. There are 2 main types of sonar, passive and active. Passive sonar listens to sounds given off by possible targets and can determine the direction in which the object is located, but not its distance. Again, passive sonar listens for sound given off by possible targets and can determine the direction in which an object is located, but not its distance. Submarines generally use passive sonar systems because they do not give any sound that other sonar might detect. Active sonar sends sound waves through the water and receives echoes from any object struck by the ongoing waves. Most surface ships must use active sonar because noise from the ship itself interferes with passive sonar. Recall the familiar ping from the sonar in movies featuring submarines? This ping is an electrically produced sound featuring wave transmitted by a sonar transducer. The transducer uses a crystal and pulses of high frequency voltage to produce the vibration that is transmitted through the water. When the crystal is subjected to pulses of high frequency voltage, the crystal will distort at the same rate as the frequency. It is the crystal It is the crystal's distortion that produces the vibration. See the diagram of the bottom of page 92. The transducer is lowered through the bottom of the ship's hull, and sound waves are sent through the water at regular intervals in bursts. If the outgoing waves electrical energy from light. Thanks to the United States space program, we can convert the sun's light directly into electricity. The invention of the photovoltaic cell, also called solar cell and photocell, made this conversion possible. The first photovoltaic cell was made from selenium, but today crystalline silicon is used. Photovoltaic cells made from crystalline silicon have a much higher efficiency than the original selenium cells. A photovoltaic cell, in figure 5-17, is constructed of two thin layers of crystalline silicon, each injected with impurities to form a negative and a positive semiconductor material. When secured together and then exposed to light, an electrical potential is developed. The layers are connected to thin wires that allow the photovoltaic cell to be connected to an electrical circuit. See figure 5-18. While a typical photovoltaic cell produces approximately 1 watt and 0.5 volts, the cells can be connected into arrays. Arrays consist of many cells connected in series and parallel to increase the voltage and current capabilities to a level sufficient to power lights and equipment. One application of power supplied by photovoltaic cells is power for a residential home. As a demonstration of this type of power, the Boston Edison Power Company built a model home powered by solar cells. The home is powered by 2 arrays of solar cells mounted on the roof. Each array contains 12 modules with 432 individual cells. The solar cells provide approximately 45% of the family's electricity. Today, solar cells are commonly used to partially power homes and heat swimming pools. The cells can also supply the complete power needs for items such as calculators, watches, and satellites. In addition, solar cells supply power for remote locations where there are no accessible power lines. See figure 5-19. Figure 5-20 shows a common solar array for providing power. Figure 5-19, solar powered radio transmitter used for highway construction. See the top of page 96, figure 5-20, a solar array. Project 5-1, bottom of page 96, the Photoelectric Controller. Try building your own photoelectric control. A photoelectric control device using a photocell is diagrammed in the project schematic. When light shines on the cell, the resistance of the circuit changes. A cadmium sulfide photocell is a light variable resistor. It is most sensitive in the green to yellow portion of the light spectrum. With it, you can use light to control many electronic devices. Photocells are used in counting operations, burglar alarms, door opening mechanisms, and in many other devices. Experiment 5-3, building a thermocouple. In this experiment, you will demonstrate and construct a simple thermocouple. Materials: 1 piece of copper wire, 1 piece of iron wire, 1 pack of matches, and 1 multimeter. Step 1. Twist one of the copper wires together with one end of the iron wire. 2. Connect the leads of the multimeter to the opposite 2 ends of the copper and iron wire. Set the meter to read voltage. Be sure to observe the proper measuring technique. 3. Light a match and heat the junction of the two wires. 4. Observe the results on the meter. Explain what you have just observed. Could you use materials other than copper and iron? The photoelectric control. The same principle of generating electricity from light is used to produce a device called a photosensitive cell. A photoresistive cells are light-sensitive resistors. Instead of providing a direct supply of electricity, this device is used to vary the amount of current that can pass through it, much like a variable resistor would do. The photoresistive cell increases circuit resistance when there is no light. It decreases resistance when there is light. The symbol for a photoresistive cell is shown in figure 5-21, bottom of page 97. 5-22 shows a small thermocouple. Electrical energy from heat. A device used to indicate and control the heat of electric ovens and furnaces is shown in figure 5-22. This device is called a thermocouple. When two dissimilar metals in contact with each other are heated, a potential difference develops between the metals. Figure 5-23. In the demonstration of figure 5-23, an iron wire and a copper wire are twisted tightly together. Their ends are connected to a sensitive meter, such as a galvanometer. A galvanometer is a device that is capable of measuring very small currents. When the flame of a lit match heats the twisted joint, a reading on the meter can be observed. This indicates that an electromotive force is present. The output voltage of a thermocouple can be strengthened